Okay, so we're actually going to do some proper iterations now, which is some of the things you should be familiar with from GCSE. So we're talking about using an iteration to find an approximate for a root, remembering that's where it crosses the axis. So I've written up here to solve f of x equals 0, in other words, to find a root by an iterative method, you rearrange your original function into a form that has x as the subject, x equals g of x. Actually, x isn't technically the subject there, and you'll see why in a second, because you can actually have x's on both sides as well, but we just want a single x equals. And then you can use the iterative formula that to find the next version of x, the next value of x in the iteration, you put the previous value of x and you put that into the function. So we're going to see why this works later on as well. First one that I've got here is we are trying to find out if we can come up with an iterative formula that we have here from this one to be transformed into this one that we've got written. So the tip with this kind of thing is that to try and take this function being equal to 0 and to make it written like this is that there's many different ways you could possibly make x the subject. So the best thing to do is to look at the target equation and to see if that can give you any clues how to rearrange. So let's have a look at the first one. We would say that it was equal to 0 to begin with, so we're going to take the first function and we're going to make it equal to 0 because that's what it's telling for us to do, and then we're going to see if we can rearrange it into the right kind of way. So we have 0 equals e to the x minus 1 plus x minus 6. So looks like there's got to be something to do with a 6 minus x. So I'm going to put the 6 onto the other side, and I'm also going to subtract the x. And that means I'm now going to have it as equal to e to the x minus 1. Looks like I'm starting to get towards this thing that I've got here. So let's take logs of both sides. I'm going to do ln 6 minus x equals x minus 1. And then I plus 1 to the other side, so we end up with x equals ln of 6 minus x plus 1. So we've rearranged that first one to make x, not the subject, but to have it as an x equals type equation, which then means we can use this kind of thing that we've got over here. The next part of this question then says that the root of g of x equals 0 is alpha. The iterative formula, x n plus 1 equals ln 6 minus xn plus 1. And it says something here that x naught equals 2. And it says this whole thing is being used to find an approximate value for alpha. Well, all I've written over here is that x naught, x1, x2 represent successively better approximations of the root, where x naught is the starting value. So they're asking you to start off this process with the first value x naught being equal to 2, and to use this formula to help you find out what x1 and x2 and x3 are, all to 4 decimal places. Now, if you're familiar with this from GCSE, this is all probably going to be quite straightforward, but I want to just talk about how this formula actually works. So if you think about it, if we're going to try and find out what x1 is, if you look at that formula, x1 is when n is equal to 0. So x1 would be ln of 6 minus x0 plus 1, which is just going to be the ln of 6 minus x0, or x0, sorry, is 2 plus 1. And so we can put that into our calculator and find out what it's equal to. So we're going to have that's the ln of 6 minus 2 plus 1. And we come up with this first approximation is 2.3863, and that's to 4 decimal places. Now, you don't want to have to now do this same process again with this number, because that's going to take ages. However, I'm going to write it out this first time, and then we're going to talk through this calculated tip. So if I wanted to find out what x2 is, x2, using this formula, that's when n is 1, will be ln of 6 minus x1 plus 1. And we've just worked out what x1 is, which is over here. Now, after you've done this, written this first substitution out, you don't need to write the substitution out again. You can actually just go straight into saying what is x2, what is x3, and then what is what is x4. Let's erase that. And the best way to do this is to use your calculator. Now, the first thing you should initially do with your calculator is you just press 2 onto your calculator and press equals. So if you press 2 and then equals, that stores the 2 as your answer. Then what you can do is just type in ln of 6 minus answer plus 1. You can recreate that iterative formula. So I'm going to do that on my calculator. ln of 6 minus answer, close the brackets, plus 1. And it should generate our first one here, which is our 2.3863. Now, because this is stored as the answer, it will go back in here like it would do, and it will produce us x2. So you should get 2.2847 to 4 decimal places if you've done this the same as me. And now you can just keep pressing the equals button to come up with the next values. So you get 2.3125 to 4 decimal places and 2.30. I think that's going to be to 50 when you round that to 4 decimal places. So if you look here, we've come up with those different iterations, we've come up with those different values. Some of the things we should notice is that they seem to be getting closer to each other each time. The jumps that they're making is getting smaller and smaller, and that's because we're trying to find the approximate value of the root. Now I've written down here on the next slide, all you really need to do is to show the substitution for x1 just to get the method mark. So when I say the substitution for x1, I just mean show this substitution that you've actually got here, that you know how to substitute into the formula. Then what we're going to do is you can just use the answer button for that. So it says you just write the final value for x2 and thereafter, as the remaining marks are just for accuracy ones. A couple of stuff that's in the side notes that we're going to start talking about. We also come across these a bit more in series as well. It says if the xn values get closer and closer together, the iterations converge to the root. I don't know why that should say so the iteration has failed. That's not right. It should say the iteration has not failed. So let's get rid of that. It converges to the root and the iteration is convergent. If things converge, it means that they all get closer and closer together. If the xn values get further and further apart, the iterations diverge. So the iteration has failed. The iteration is divergent. So if we just pause there for a second, and if we have a look at the one we just did, it looks like they're getting closer and closer together. So we would say here that they are converging to the root. And if you actually just keep pressing equals on your calculator, and you just keep going and going, you should eventually find out the calculator will stop changing the value. My one that I seem to have ended up with is 2.3065586641, and that's the root that it's going to be converging to. Sometimes it will not converge, it will diverge, meaning it gets further and further away. Last of all, it says here, if they bounce back and forth between values, we say that the iteration oscillates, or is periodic, or is non-convergent. Oscillate should remind us of the sine graph that we say like oscillates up and down. Periodic also means it repeats itself over a particular period. The easiest one to remind yourself though is if something is not convergent, you can just call it non-convergent. Okay, if it's just, this is the one that matters for it to go to a particular value. If it doesn't, you can just call it non-convergent. So I am going to give you a bit of a chance to have a go at doing this question here. So if you want to pause the video here and have a go yourself, I'm going to go through it in just a few seconds and see how that goes. Okay? Okay, so sometimes these can actually be quite difficult to do, so you really should look at the thing that you're aiming for. I would actually manipulate this thing first. So I would think to myself, I'm going to actually go in reverse for a second. I'm going to square both sides so that I get x squared equals, and I'm also going to multiply out this top part here. I'm going to get 12 minus 4x all over 3 plus x. So when I multiply that up, you're going to get 3x squared plus 3x cubed equals 12 minus 4x. This is my kind of side bit of working that I might do, and actually that's now going to help me to think how I can go backwards. So it looks like what they did is they actually made this bit the subject first, and then they did some factorizing. So my answer for part A of the question would have looked like this. I would have started off by saying 0 is equal to x cubed plus 3x squared plus 4x minus 12. and my sneaky working backwards tells me what I'm going to do is put the 3x squared and, oh, did I say I had a 3x cubed there? That shouldn't have had a 3 there. I'm going to put the 4x and the 12 to the other side, so it becomes a 12 minus 4x equals x cubed plus 3x squared, and then I'm going to factorize. So I get 12 minus 4x equals, and looks like I factorized out an x squared, so if I take out an x squared here, I'm going to get an x plus 3. Then I'm going to factorize this as well and divide by the x plus 3. So if I factorize this, I get a 3. Oh, not a 3 there, silly me. I'm going to get a 4, that's the common factor, and I have a 3 minus x, and that's being divided by this bit here, which is x plus 3, but look, they wanted it as a 3 plus x, so I'm just going to switch that around like this. That's equal to x squared, but I'm going to just go straight in with the square root sign there and say that's what x is equal to. So this is quite hard to do just by guessing, so you might like to actually start rearranging this one to see how it looks like this one here. Okay, it says that it has a single root which is between 1 and 2. They're not asking us to prove that it's between 1 and 2 though. So use the iteration formula, x of n plus 1 equals square root of 4 brackets 3 minus xn over 3 plus xn. So these two bits here are where you're going to be putting into your calculator the answer button, okay? x0 equals 1. Find to 2 decimal places the value of x1, x2, and x3. So for part B of the question, I'm going to do for my value of x1, I'm actually going to show the substitution to get that method mark. It's going to be the square root of 4 brackets 3 minus, and it says the starting value is 1, and that's all going to be over 3 plus 1. But what I'm going to type into my calculator is I'm going to press 1 equals to get the answer, and then I'm going to say 4 brackets 3 minus answer over 3 plus answer, and then I can just keep pressing equals to find these values. So I'm going to go into my calculator and I'll press 1 equals so that it is stored as the answer, and then I'm going to set up that fraction that I've got there. Okay, so let's see what this is going to write. So I've got the square root of a fraction, 4 brackets 3 minus answer over 3 plus answer. So that looks like my value for x1 is root 2, but it wanted it to 2 decimal places, so I better give it to them in how they wanted it, which is 1.41. Now I can just go straight in with my calculator. x2 is going to be 1.20 to 2 decimal places, and pressing equals again, x3 is going to be 1.31 to 2 decimal places. And it says by choosing a suitable interval, prove that alpha equals 1.272 to 3 decimal places. Well, if you keep pressing equals on your calculator, you will find that this is the root. However, it's asking for us to use a suitable interval and to prove that this is correct to 3 decimal places. So what that means we're going to need to do is what we did much earlier on. We're going to think of what are the things that round to 1.272. So I'm going to go and put into my function 1.2715. I've gone 0.5 down, and I'm not going to be putting this in here. I'm going to be putting this in the function that we have that's at the top. So I'm going to actually be doing 1.2715 cubed plus 3 times 1.2715 squared plus 4 times 1.2715 minus 12. Now you don't need to write all of that out, but I just wanted to make it clear what I was actually doing there. So I'm going to got my 1.2715. I'll store that in my calculator as the answer, and I'm now just going to have answer cubed plus 3 answer squared plus 4 answer minus 12. Saves me doing some typing, and we get a very small value. We get minus 8.21 times 10 to the minus 3, which is less than 0. And I'm also going to put in my other part, which is 1.2725, so I've gone that 0.5 up. I'm not going to show the whole substitution this time. 1.2725. I'm now going to say that that is my answer cubed plus 3 answer squared plus 4 answer minus 12. Let's hope it's positive. Yep, it is 8.27 blah 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 times 10 to the minus 3, which is greater than 0. So we can say here, change in sign, f of x is continuous. Whoa, not getting used to this new pen. F of x is continuous. So root is 1.27223 decimal places. Okay, hopefully you got that one right. Now let's have a look at why this method works. So there are a few different ways that you can come up with an iterative formula, because all you really need to do is to make x the subject. So one of the ways we could do this, I have x squared minus x minus 1 equals 0. There's a pretty easy way we could make x the subject. So my first way I could do this, let's do this one, let's see if I can do them all in different colours. So way number 1. The easiest one, I think, is we can just rearrange it so that we get x equals, adding this to the other side, x squared minus 1. Right, let's do another colour. Let's do, all these colours are horrible. Let's pick a different one. Let's do a green. Way number 2. Oh, excellent choice there. Way number 2. Okay, I think the way I might spot about doing this is I could say, well, x squared is equal to x plus 1. So that must mean that x is equal to the square root of x plus 1. Now, way 3, I'm wondering if any of you can spot way 3. Way 3 actually took me a bit of time to think, how's that final way I could do this? Look at me making a mess of all this stuff. Let's erase this. Now, the way I would do way 3, and I've only noticed there's this pattern, is it's stuff to do with factorising. Now remember, we're not trying to factorise to solve, we're trying to factorise to find x as an x equals. So I have started off with x squared minus x minus 1 equals 0. I'm just going to factorise these two bits here. So I get x brackets, x minus 1 equals 0. So that's x brackets, x minus 1 equals 1. So x equals 1 over x minus 1. So the three things that we've got here, our iterative formulae, we have this as an iterative formula, because it says x equals. We have this as an iterative formula, and we have this as an iterative formula that we've got here. And we're now going to try and explore why this iteration method even works, and how you have to be careful with what you're using, okay? So let's scroll down a bit, and we're going to look at something called staircase diagrams. So we've been asked to solve this equation. This was the same equation that we had to begin with, and what we could do to try and make it as an x equals, one of the ways we did this was an x equals the square root of x plus 1. Let's just have a look and see if that was what we got. Yep, it was the green one here, x equals x plus 1. So I'm going to do this question in green to remind us that's what we're looking at. Still getting used to my new board setup here. Okay, so we're going to do something that's called a staircase diagram. We can then use the recurrence formula for this, xn plus 1 equals the square root of xn plus 1, and we want to see why it works. So if you think about this for a second, the solution of x equals the square root of x plus 1 is the same as sketching y equals x and y equals the square root of x plus 1 and seeing where they intersect. So if we're trying to solve this thing being equal to 0, because of our rearranging, it's the same thing as finding out where these two things cross, because it's the same as having y equals x, y equals the root of x plus 1, and making them equal to each other. So in order to do this bit, I'm just going to scroll down just a little bit more so it's on the right page. We are starting off with a particular value for x0, and we are going to say for x0, you would take that value of x0 for this recurrence formula and you would substitute it into here. So for the diagram, we're going to go from this point here, and pardon my lines not being very clear, I wonder if I can do a better tool for this actually. I wonder if shapes has got what I'm looking for. Insert line, great, here we go. So I'm going to go from x0 up to the curve. This would then be my new value for x. okay? But to find that new value for x, I'm going to go across to the y equals line, and you'll see that that value for x is about 1.4, which is the same as the y value. So that's what we usually do. You would then take this new value here, which is actually x1, and you would put that into the curve, and the value for the curve that you get there is when you go straight up to the curve. That now gives you your next approximation as about a 1.5. So to get that as an x coordinate, I'm going to go across, and again you'll see that's corresponding to the correct x coordinate. Now you can see what happens here. Each time you do an iteration, you get closer and closer to the correct route that we have here. So this is called a staircase diagram. I'm just going to go through what I did there one more time. We start off with a given particular value for x0, and usually what we would do if we were doing this without a graph is we would substitute x0 in here to find out what the next x value would be. Now graphically what that means is going from x0 to say from the curve, the blue one, which is the thing we would substitute into, what value do we get for the answer? And the answer we can put back in by using the y equals x line, because we're saying that the answer is y, but I want to be substituting in an x value. So we then go from the curve, we bounce back to the y equals x, then we go to the curve again, y equals x. That's the repeated position. The lines going up means substituting into this part, the right hand side of the formula. Going across is the thing that takes the output, the y coordinate, and changing it to an input. Taking the output and changing it to an input. That's what y equals x is actually doing for us here. So this is an example of a staircase, and it converges to the root. Okay, so this one is a staircase that does converge to the root. There are a couple of other things that can happen here. So this is one of them that shows why it does work. Okay, then we can sometimes have something called a cobweb diagram. Now, for the cobweb diagram, we have taken this equation and we have rearranged it in a different way to x equals 1 over x minus 1. Well, which one was this? It was the one that we did in black down here. So we're going to do the same thing that we had before. We're going to go to where x0 is. We're going to go straight down to the curve, and then we're going to find out what that y value is, and then we're going to find out what the x one is that corresponds. So these can be a bit confusing to begin with, but once you've done some practice, I think you'll find them fine. So we're going to start from x0, and we're going to go straight down to the curve, and that gives me an input value on the y-axis, whatever this one is down here, which corresponds to this one. So you go from the curve across to the line, then you're going to go down to the curve, then you're going to go across to the line, then you're going to go to the curve, then to the line, then to the curve, then to the line, then to the curve. And you can see what happens here. It's going to do this spiral that comes around like this, and we call this a cobweb spiral. It spirals inwards, and it looks like a cobweb, you know, those things that spiders make that go in the corners of rooms and things like that. So this one does also converge to a root because it's got that pattern. Now, if you're not so sure about what's happening with this pattern, I've got something on the next slide that should help you. But really what we're doing is we go down to the curve, across to y equals x, down, across, up, across, down, across. It's only up and down, and you always start off with the curve, and then you go to the straight line. So it works. Both of those iterative formulae both work. They will both converge to one of the roots. Okay, this one seems to have converged to a root that is on the negative part. It's going to be like a negative 0 point something. And actually, if we look at this one here, it looks like it's going to converge to one of the positive roots, because obviously it's a quadratic equation. There's going to be two particular roots that we've got here. Okay, so we're going to look at the last one. The last one I think we did was in this pink colour. So let's have a look at the pink colour. And this is going to be one where iteration actually fails. So let's put it in this pink colour. So one of the other ways we could have rearranged this was we could have said that x was equal to x squared minus 1. That's what we said with the pink one. So we're going to use this recurrence formula and see what happens this time. So I'm going to go from x0. Now remember, you go to the curve to begin with, And then after the curve, you need to go to the line. Well, I can't go left to the line. I've got to actually go right to the line. And when I go right to the line here, I get to this. You can see what's going to happen here. I'm then going to go up to the curve. And actually, if I wanted to go across to the line, it's going to go all the way over there. And you can see that this pattern is going to get further and further apart because of the shape of what y equals x squared minus 1 looks like. So this is an example of a staircase diagram that fails because the root, in this particular case, the root, not the root, sorry, we should just say that the iteration diverges. Let me get my proper colour here. So we should say here, the iteration diverges. And you get that sense of these staircase diagrams getting further and further away from each other. Okay, so let's have a look at you having a go at this, and then after I've gone through this one, you can have a go at doing some of the questions from exercise 10B. So I'll give you a moment to pause doing this, and then I'm going to go through this one myself. Okay, so let's actually do the whole question that we've got here. It says f of x equals x squared minus 8x plus 4. Show that the root of the equation f of x equals 0 can be written as this. Well, you can see what's going to happen. If you square both sides, you're going to get your x squared equals 8x minus 4. So it's quite an easy rearranging one for part A here. Part A, let's show then we can do that rearranging. Let's make f of x equal to 0 to begin with. And I'm just going to put the 8x minus 4 on this side equals x squared. So x equals the square root of 8x minus 4, as they wanted. Now part B says, using the iterative formula and starting with x0 equals 1, draw a staircase diagram indicating x0, x1 and x2 on your x-axis, as well as the root alpha. So there's a little bit of extra here that we might need to do. Let me just get my line tool that I wanted here, which I shall do in my blue to match what we've got going on. So, quick reminder, you start at x0, you go curve, line, and it's always up and down, across, up and down, across. So the x0 they wanted us to do is to start at x0 equals 1. So here is my x0 equals 1, and we're going to start off going here. We're then going to come across, and that is now going to hit down here at what we think x1 is going to be. This was x0. And I'll add these on afterwards. This is going to be x1. We're then going to go to the curve, and then we're going to go across, and this is going to be x2. If we wanted to keep going, we would go to the curve, and then x3, to the curve, x4, to the curve, x5, to the curve, x6, and eventually you can see it's going to converge to this root that we've got here. So let's finish the question off by actually labelling these things. This is where x0 is. By the way, x0 was here because it said it was 1, just in case you didn't spot, the axis goes between 0 and 5 here, so that must be where 1 is. So this one is going to be where x1 is. This one here, pardon my slightly wonky line drawing here, it's quite difficult on this. And this is where x2 is. If you wanted to, which we don't need to do, you can keep going here, and you can see that that's roughly what we think x3 should be. I'm also going to do this iteration for a second, because I actually think it would be useful for you to see what happens. So we've said that x0 is equal to 1. I'm actually just going to go through the values by using my calculator. So I'm going to put 1 in my calculator, and I'm just going to do the square root of 8 answer minus 4. You can see that x1 is equal to 2 when I do this on the calculator, which it is. We then get that x2 is equal to 2 root 3, which is 3.46, which is roughly what mine is here. If we keep going, x3 is equal to 4.869, so yeah, it's roughly around where 5 is. Just write that down, that's 4.869 or 4.87. I'm just going to keep going for a second. x4, that's 5.91. Let's just keep going until I get to what I think the root actually might be. I'm just going to keep mashing equals. Looks like it's going to be something like 7 point something. Great, I've pressed equals a good few number of times now. It looks like the root is actually going to be 7.46. So these diagrams people do find tricky. This memory thing that we've got down here is going to be the most useful thing that we've got if you find it a little bit confusing, which is very, very understandable. So have a go at exercise 10B, and then in a moment I'm going to go through some exam questions with you.